Okay. Now let's look at solutions in R2. Okay. And the main idea here is that we're going to take v of x1, x2, t to just be a solution to an equation where I can allow u to be independent of x3. Okay. So that's the idea. I set up my initial data so that I can use that R3 solution, but my resulting solution is going to be independent of R3. Okay. So I will integrate out R3. Okay. And to start doing that, I take phi and psi in R3 independent of x3, okay? And I'm gonna essentially project the spheres that I'm integrating over to disks, okay? So S of CT that I started with, I will think of them as two-dimensional balls centered at x CT, okay? So this is going to be a disk with radius CT centered at x, right? So then in this case, my v, well, I'm going to write that as a vector. My v is, write it just as a function of xt. This is equal to 1 over 2 pi c, the integral over b xct psi y divided by c squared t squared minus x minus y squared to the 1/2 integrated over y plus dt 1 over 2 pi c times, drop down a bit, the integral of b x ct phi of y dy divided by c squared t squared minus x minus y squared to the 1/2. Okay, so v now is going to depend on values of phi and psi inside of b of xct. Okay, so notice now that these are volume integrals, right, over the inside of the disk. And so this process of projecting means that, you know, I've taken a sphere and I've projected it down to a disk, which means that that shell has been projected to a disk volume, okay? And so now everything inside of this disk matters. And that's the cause, essentially, of Huygens principle essentially not holding for n equals 2, because I can no longer say that just the leading edge of the wave is what matters, okay? The inside of the wave matters too, okay? And so I'm not going to get this nice interference cancellation of spheres that, you know, at the leading edge of the shell in this case, okay? And so So just to sum up, right, with the wave equation, okay? So it is the prototypical hyperbolic equation. It has two families of characteristics, okay? Remember, you have characteristics that go that way and characteristics that go that way. And as a result of that, we have finite propagation speed, okay, which is physical, although note that when we get to the heat equation, we're not going to have finite propagation speed of solutions. We'll talk about later. We can get explicit solutions, okay? We've talked about the importance of the domain of dependence, okay? And these sort of facts here are sort of the result of having a finite propagation speed, okay? We talked about conservation of energy, okay? Conservation of energy essentially allows us to work out some uniqueness results. We've also talked about regularity, okay, and how compact support is translated as you move forward in time. So as opposed to the heat equation, how regular your initial conditions are is how regular your resulting solution is going to be. There's no smoothing involved. Everything just gets propagated, right? It's not going to happen in the diffusion equation. The diffusion equation smooths things out. And you have C infinity solutions, even if you start with, you know, piecewise continuous solutions on the boundary. And the region of support of your initial condition essentially gets, you know, propagated according to your characteristics. Okay. So that's the wave equation. I have maybe about 8 allotted minutes left.